So today we're going to gain some intuition behind an RHP 0 that is very commonly associated with a common source stage when using a Miller cap. So over here we have a common source stage with a transistor, with an NMOS transistor with transconductance of GM, and then additionally we have a Miller capacitor between the gate and the drain of this common source stage. So just to gain some intuition, a feed forward path usually leads to zeros. And what this means is that if you have a feed forward path between the input and the output of an amplifier, you are probably going to get a zero. Or it can be something that is associated with zeros. And so just looking at this circuit very intuitively, we see that there's a regular path that is formed by this transistor between the input and the output. But then additionally we get this cap. And we know that with caps at higher and higher frequencies, they start looking more and more like shorts, which means that there's going to be another path directly from the input to the output that kicks in at a higher frequency. So even examining this structure, we can see that there's a high probability there's probably going to be a zero associated with this particular circuit. And so that's kind of what we want to derive. What exactly does that look like? So because we want to see this analysis in the current domain, we are going to short this output from a small signal point of view to ground. And this will allow us to figure out just exactly what the current contribution is from this GM stage, and then what the current contribution is from this capacitor stage to the output. So just because of superposition is completely fine to be able to ground those. So in order to proceed with that analysis, we need to define what the current direction is. So let's just assume that I out is in this direction to ground. It doesn't really matter what it is, but you can choose either one. But just for the sake of it, we're going to choose I out being in this direction, which means that GM is definitely negative, and then this capacitor as defined in this direction is positive. So it's going into V out, and this is coming from V out. So we can use that to come up with a very simple set of equations, which is that I out is going to be the contribution from the transistor, which is GM V in, and there's this negative sign. We get this negative sign just because this polarity is opposite. Plus the contribution from the capacitor, which is V in SC. And then we don't have a negative sign for this term because we've defined the direction to be going into the output. So if we were to simplify this down to get the transfer function, which is I out upon V in, we'd get something that looks like minus GM multiplied by 1 minus SC upon GM. And so this equation intuitively makes sense for sure. The reason being that this is the contribution, this is the transfer function at DC, which is just coming from the GM stage, so it's just coming from the transistor. And then this is a term that kicks in at a higher frequency, and then this is the zero. Now why is this a right half plane zero? We can see that by going down here and then just drawing on an S-plane what this looks like. So a zero is when the numerator of an equation is equal to 0. So that means that 1 minus SC upon GM is equal to 0, which means that S is equal to GM upon C. So in the on the S-plane, this winds up looking like a 0 at GM upon SC, and because this is in the right half plane, it's automatically a right half plane 0. So the equations definitely prove out that we have a right half plane 0, but what we want to do is we want to get some intuition. What is going on that is causing this right half plane 0? And thankfully for this circuit, it's quite easy to get the intuition. And to get the intuition, bode plots are our best friend. So let's look at what the transfer function looks like. So this would be I out upon V in magnitude, and then this is I out upon V in phase. We want to look at both. So this is omega. And just to make things simpler, let's do some color coding. So our MOSFET curves are going to be represented in green, and then let's make our capacitor curves be represented in brown. So first, looking at the MOSFET, what is I out upon V in? So what is I out upon V in coming just from the MOSFET? Well, as we've defined in this direction, it's just minus GM, right? And it's completely frequency independent. There's no just for this MOSFET current, there's no frequency dependent. It's just it just looks like a transconductance. But the thing is that we can't really have minus over here because this is just magnitude. So we have to keep this positive, and we have to represent the magnitude in the phase response. And how do we do that? Well, we just say that it's equal to plus 180. And why does plus 180 represent minus 1? It does so, well, we can just gain some intuition behind that over here. So if we have, using Euler's equation, if we have plus or minus 180, that would be e to the power j pi, which is also equivalent to e to the power minus j pi, which is equal to minus 1. And why is that? Because if we expand this out, we get cos of pi plus j sine of pi. Well, this term is 0, and this term is minus 1. And the same thing would hold if these were negative signs. So that's just an aside. But so then you get this contribution. Now let's look at the capacitor. So for the capacitor, I out upon V in looks like something that's quite low at low frequencies and then monotonically rises up, assuming that we have a log-log plot. It just keeps on rising up at higher and higher frequencies. So, and this completely makes sense because at infinite frequency we expect the output current from this to be infinite because it would look like a short. And now what about the phase? The phase would start off at, actually the phase would continuously be at plus 90. And why is the phase at plus 90? We can also look at that over here. So the contribution from the cap to the output current is equal to SC. That's just basically the inverse of the impedance of the cap. So what this means is, because this is in the numerator, that always translates to a plus 90 degree phase shift, which we can see if we look at the S-plane. We get this 0 at the origin, and so as we traverse our j omega axis, we see that this always remains plus 90 degrees. So that's just a quick aside about why we get plus 90 degrees. So these are the individual contributions to the output current from the capacitor and from the transconductance. Now what does a composite plot look like? Well, let's draw that in blue. So that's our little legend over here. So at low frequency, it's just going to look like what GM is. So it's going to follow what the contribution from the capacitor is. At higher frequencies, it's going to get dwarfed by this contribution from this guy, which is the capacitor. So it's just going to look like something that starts out flat and then starts rising. Well, what is this? It's a 0, right? And what is the 0 frequency? The 0 frequency is, as a rule, all poles and zeros occur when different quantities become comparable. So, which means that in this particular case, the current contribution from the cap would be equal to the current contribution from the transistor, which means that SC would be equal to GM. So that what would that happen if we said S is equal to j omega, then omega magnitude would be GM upon SC. So this is just GM upon SC, GM upon C, I'm sorry, the frequency at which this occurs. So immediately we see that this ties in with our equations over here, which we're also predicting a frequency occurring at GM upon C. Now what does the phase look like? Well, the phase is going to do the same thing. At low frequencies, it's going to follow the MOSFET, and at high frequencies, it's going to follow the capacitor. And then at this corner frequency, that's going to be where it transitions. and the transition is going to be 135 degrees, because the total difference is 90 degrees, and then at the quantum frequency it's 45 degrees. So this is a right half plane zero, because the magnitude response rises and the phase falls. And this is an aside for a different topic, but that just spells really bad news for control circuits, because you get magnitude that is rising, but then you get more delay, so that can lead to instability. But hopefully this video gives a quick intuition behind right half plane zeros, why they occur, and kind of graphically how they come about.